Think about how you learn to recognize handwriting. Nobody handed you a rule book explaining that an A is a closed loop with a small vertical line on the right. You just saw hundreds of letters, and your brain quietly built its own sense of what an A looks like in all its messy variations. Machine learning works the same way, but traditional programming does not. Standard code relies on explicit, rigid rules, definitions that have to be exactly right every single time for the computer to understand them. The problem is that human expression doesn't follow a geometry textbook. If a writer slants a letter or leaves a loop slightly open, the rigid code sees a failure, leading to a total rejection of the sample. To account for every possible variation, you would have to write a new rule for every person on Earth. You quickly end up with an infinite contradictory rulebook that is impossible to manage. This forces us to find a different approach. How do we teach a machine to handle a task that is too complex for a human to explicitly explain? Trying to capture the nuance of a handwritten letter with rigid code shows us the limit of traditional programming. Logic alone cannot account for the infinite ways humans express themselves. This is where machine learning takes over. Instead of following a list of instructions, the computer improves its own performance by studying data. We see this most clearly in the way your email provider filters out spam before it ever hits your inbox. In this world, data is the textbook. We show the filter a massive pile of real emails, labeled spam or not spam. More data isn't always better. A small set of clean examples is far more effective than messy information. Because the machine learns from these examples, the quality of this textbook determines exactly how smart the system can eventually become. Once the data is ready, the system begins training. The algorithm scans the labeled examples over and over, slowly adjusting itself to get better at predicting the right answer. During this process, the system finds connections humans might miss, patterns in phrasing or behavior no programmer could write. After training comes the test. We show the system brand new examples it hasn't seen to see if it categorizes them correctly. This phase is vital because it proves the system has actually learned a universal pattern, rather than just memorizing the specific emails it saw during its training. We measure this success through accuracy. If a filter identifies 97 out of 100 new emails correctly, it's 97% accurate. The goal isn't absolute perfection, but a tool that is reliable enough to be useful. Real intelligence isn't measured by what the machine has already studied, but by how it handles the information it hasn't seen yet. The final product of this process is the model. This is the trained system that is now ready to make independent predictions in the real world. This is why your spam filter catches tactics it's never encountered before. It doesn't need to see a specific trick to stop it. It understands the underlying behavior of what spam looks like. This move away from hard-coded rules and toward recognizing patterns changes our relationship with technology. It makes our data the most valuable resource we produce. Every message you send, every photo you share, and every search you perform serves as a set of examples. Together, these actions form a global digital textbook that machines use to study us. This leads to a final, inevitable question. What kind of models are being built right now using the data you generated today?